So let me start then today's lecture. I first wanted to make a correction. Somebody kindly pointed out I was making an error at the end of the last lecture. So let me just go through that bit again. So what I was saying, as a consequence of the axiom of replacement, so remind ourselves what that means. The axiom of replacement, right, that says the action of a function on a set gives you a set. So f takes sets to sets here. Well, the assumption is that, sorry, no, that's the wrong thing to say. For any function f, if x is a set, the range of f on x is a set. Yeah, and of course this is just the collection of y's for which there is a u in x, such that f of u equals y. So the idea was that you could take a bag of elements in x here, and you replace each one by something else according to the function f, and you end up with a set here. All you've done is just change these elements for something else according to the prescription of f. It hasn't got any bigger. It's still a set. So I just wanted to point out, right, that this implies if I've got a function if f is 1 to 1 and f goes from x, sorry, from the ordinals into x, then x cannot be a set. It must be a proper class. Here. And the reason is if we the axiom of replacement. If x were a set, right, and let's say y contained in x, y is the range of f on the ordinals, right? So it's just the range of the function here. Then y is a subset of x. And f is now a one-to-one function that's onto y. That's a bijection between the ordinals and y. So then if I invert f to the minus 1, right, and I apply it to y, the axiom of replacement tells me that this is a set because y is a set. But in fact, it's a proper class by Burali 40. This contradicts Burali 40. that says that ON is a proper class. Here. So I can't have a one-to-one map of the ordinals into any set X here. Actually, I mean, we can then deduce from this that the cardinals form a proper class. Card, this was we defined to be, this is the collection of alpha, such that alpha is a cardinal. Let's say is an infinite cardinal. This is a proper class, which we proved already. And we enumerate, because we could enumerate card, we had this function, the Aleph function, that gave us, for any tor, it gave us the torth cardinal here. So the collection of all the Aleph tors is card. So this function here is going from all ON to card, or at least the ones that are not finite, right? The ones that are omega or beyond. So actually this is then a bijection, right? So again, by the axiom of replacement, this cannot be a set. It's a bijection because we use the ordinals to count the infinite cardinals. Cannot be a set. I should be saying the cardinals above omega, minus omega. Okay, I think that's all I want to say about the replacement at the moment. Any questions about that? Okay, if not, then we'll move on to the axiom of choice, section 4.2. So the axiom of choice, this is, as I say in the notes, this is kind of ubiquitous in mathematics, often unspoken, but it's lying there doing some work. If you want to show that certain vector spaces or so-called Banach spaces, which may be infinite dimensional, if they've got a basis, then you'll need the axiom of choice to do that. If you want to show that there are maximal ideals in rings, you'll be using the axiom of choice to do that. Often, though, the axiom of choice is not used in the form of the well-ordering principle, which is how we first introduced it, but it's used as we should define it, as a way of choosing elements from sets. But actually, more likely in algebra and elsewhere, it's used in a form called Zorn's lemma. So we're looking at these different versions of the axiom of choice in this section here. The well-ordering principle was necessary really to get a nice clean theory of the cardinals off the ground. Because we can well order any set, that also means that we can biject it with an ordinal. And that is very useful because then we can say the cardinality of the set is the least ordinal it's bijective with. If we weren't able to find bijections between sets and ordinals, the theory of cardinals then becomes a tricky business indeed. And indeed, then cardinals don't become linearly ordered. So set theorists usually are assuming the axiom of choice is true in the V hierarchy. So what we're going to do is look at the kind of traditional AC axiom of choice form first, and then later, or perhaps next time, go on to Zorn's lemma. So the definition of AC is the bottom of page 56. And the idea is I've got a set G here, and it consists of non-empty sets. A choice function for G is a way of choosing an element from each of these sets. Or why it's called choice, chooses. From each of these sets. So it's a function f, so that for any x in the family of sets G, f of x is a member of x. And this is the only reason we insist that G consists of non-empty sets, so that there is something to choose. So it goes through each set here and picks out an element. So the axiom of choice just says that in every case of a G like this, there is a choice function. So for every family G of non-empty sets, there's a choice function f for G, so that for all x in G, f of x is a member of x. So it's not clear, just on the basis of set theory, perhaps why choice functions should exist. I mean, there is something to assert there, right? We are asserting the existence of this way of choosing something from each set. Now, if G is finite, only contains finitely many sets, we can always do a finite amount of choosing. I can just take one element from this set and another element from this set. I can do that because they're non-empty. I could do it for 3 sets. I could then pick another element of a third set. For any n, I could always pick for n sets one element from each. But as soon as G has got a mega many sets in it, you're asserting the existence of a function whose domain is omega and can go around and pick an object from each of these sets. So that is an infinitary assertion about the existence of sets. The finite case is no more problematic than saying, if I've got elements, u1 up to un, then there's a set which consists of u1 up to un. Right? So it's a little bit of just pair set axiom, right? And perhaps unions if you're making it larger. So I can always make a finite number of choices using the axioms I've got. But if I want to make omega many choices or more, if the cardinality of G is bigger, this choice function has to come from somewhere. So we posit the existence of such a function in this axiom of choice. So if I've just got finitely many sets here, then in the end, there's no problem in picking elements or picking or choosing. If G were finite. It's when G is infinite. So when the cardinality of G is at least omega, so we need to invoke the axiom to declare we've got a choice function. Okay, so that's the idea behind AC. And so Zumelo showed that AC was equivalent to so this was 1908. So theorem 5.1 in the notes, that AC is equivalent to the well ordering principle. I mean, indeed, at that point, when Zumelo kind of isolated this axiom of choice, a lot of mathematicians were a little bit dubious as to say, where is this? It's just an existence claim, right? You haven't constructed this function, right? You've just asserted that there is this function there. So Zumelo went about trying to actually prove the axiom of choice. And what he could do, in fact, was to actually just show that it followed from the well ordering principle. So his proof, in inverted commas, the axiom of choice, was actually a proof that WP implied AC. But we now know AC implies WP as well, so they're kind of on an equal standing. And we can't prove either of these from the rest of the axioms. Right? This can be shown. But at the moment, let's concentrate on this equivalence here and see why it's true. Are there any questions about the ideas so far? Okay, so left to right, we'll assume AC. Right, so this is the longer, harder direction here. And we take a set Y. I'm just going to go through the proof in the notes here, so I'll try and keep the notation the same. Excuse me. So let Y be any set. and we want to well order it. Right, for the well ordering principle to hold for this y. So we'll assume y is non-zero. Because trivially the empty set is well ordered by the empty relation. So we'll assume y is not the empty set. So the G that we're going to apply the axiom of choice to, this will be all the non-empty subsets of y. So let G be the collection of subsets of y which are not empty. So this is just the power set of y minus the empty set. Now this is a collection of non-empty sets. By the axiom of choice, there's a choice function for it. So we're going to parley up this choice function into a well ordering. Question is how to do it. So I let f0 be a choice function for G. So we'll do a recursion, and the recursion will just enumerate for us the elements of y. So as a device, we'll just pick some element not in y. Y is a set, so there are some things, it's not V, so there's something that's not in Y. Now we'll define F, which is going to go from V to V, to which we can apply the recursion theorem. We're going to define f of t to be just f0 of t if t is in G. So if it happens to be one of these sets. And for all other t's, it'll just be u. So the only point of this was to get a function from all sets to V. So for most sets, of course, it just defaults to this chosen u. That's not in Y. So now we're defined by recursion function h so this is going to go from ordinals to sets. So h0 of psi, we're going to apply f to the set y And we'll take away all the things that we've previously enumerated. So here in this notation, we're defining H0 of psi, and I'm assuming we know H0 zeta for any zeta less than psi. Right? So this is in the format of defining something by applying a function to the initial segment we've already defined. So in this case, it's slightly more elaborate. We take the initial segment we've defined, we take it away from y, and if this is non-empty, we can apply f0 to it. On the other hand, this might end up being empty, in which case f will return u. But either way, it's defined here. Because, I mean, yes, I mean, the empty set is not in G. So f of the empty set is u. Yeah. But it's slightly jumping ahead. Right? So, I mean, in case we're curious, what is H0 of 0, the beginning? Well, that's f of y minus, well, let me write it out, but of course, it'll be the empty set. This is the empty set. So taking the empty set from y is just y. Y is a non-empty subset of y, so this is just whatever this choice function gives me here, something in y. So H0 at 0 picks out an element of y. And H1 is going to be the choice function applied to y minus this thing we just picked out. So the idea is we now have got a process going, right? Here is y, right? And it's got all of its non-empty subsets. So what the choice function does is just pick something out here. So f0 of y, and we're going to call that h of 0. And then we pick out, oops, over here, h0 of 1, right? Something else. We take these two away from y, and we apply f to everything that's left, and this will give me h0 of 2. So this way we can impose a well ordering on y. We just go through eliminating things one by one, right? By the use of the choice function and the recursion theorem. Right? So we're using this choice function all the time, right, to work our way through y like this. To work our way through y, enumerating elements. Okay, so this is kind of a note about what's going on right here. So there's a question, surely it should be that all the x in y where x is non-empty rather than y. Not quite. G, remember, is the collection of all non-empty subsets of Y. Y is a non-empty subset of Y. So Y is in G. Right? So the choice function is acting on G, right, rather than Y. But the effect of repeatedly applying the choice function is to work our way through the elements of Y. Right, I'm hoping that that's a sufficient explanation. Okay. So note to the chat question. The choice function is a choice function for G. And this was the collection of non-empty subsets of Y. Yeah.
Sorry, Philip, you wrote earlier that it was Y is not equal to the empty set. Is it X or Y, or are they just?
I wrote earlier. Did I?
It was right at the start of the proof.
Was it? Trying to find this piece of paper now. In which case I made a mistake. Here we are down here somewhere. Yes. That was wrong. I should have written G is the collection of non-empty subsets of Y. Thanks. Good. Yes. Yes, Ryan. That's exactly what I should have written. It was an X here. It's correct in the notes. So the non-empty subsets of Y, and our choice function picks out elements from that. Okay. Okay, so here's our primary definition, H0. So eventually we're going to exhaust Y by doing this. We'll have enumerated all of the elements of Y, and there'll be nothing left. So then the function f applies to Y minus, well, everything that's in Y. So it ends up applying f to the empty set. Right? But that's all right. F is not the choice function f0, which only applies to empty sets. F of the empty set defaults to U. So that's a signal when we've exhausted Y is when the f function and thence the H0 function returns U, because then we know it's chosen something that's not in Y. That was why we particularly insisted that U is not a set in Y. So as soon as the H0 function returns U, we know it's exhausted Y. And now we've imposed a well ordering on Y, given by the stages of this enumeration. And our job will be done. So officially, so by the theorem on transfinite recursion, on the ordinals, there is such a function h. Here. So h, what is it doing? It's sending the ordinals to y together with this default set u. Of course, once it starts returning the default set u, it will continue to do so, because y has been exhausted once and for all. So we claim here then there's an ordinal such that at this ordinal beta we get u. So, and the notes make the point that the claim amounts to saying that sooner or later we'll have exhausted y. Sooner or later we shall have exhausted y. And f returns u. And now it's the argument that I was correcting at the beginning of the lecture.
Sorry, Philip, could you please put the last of the
Last bit back.
last sheet?
Sure.
Great, thank you.
Okay. So, I mean, if we didn't, if this never happened, what is H0 doing? It's going through all of the elements of Y one by one. So it's giving us a one-to-one function from the ordinals into Y. So if this didn't happen by the argument at the beginning of the lecture, right, the inverse of H0 and its range will be a map of a set into the ordinal, onto the ordinals, which is a contradiction as the ordinals are a proper class. So suppose this didn't happen here. What is H0 is a one-to-one function sending ON into the set Y. I emphasize set here. Whilst this is a proper class. But then the range of H0 is contained in Y, and so is a set. As H0 is one-to-one, I can say H0 to the minus 1 takes the range of H0 here onto the ordinals. And this is the contradiction that we saw at the beginning of the lecture. We've got a set being sent onto the ordinals. But the axiom of replacement says a function on a set is a set. Here. So there is such a beta. Okay, so when we arrive then at this least beta, I think I call it in the notes, so that h0 of alpha is u, it means it took me alpha steps to enumerate my way through y, and then at the alpha stage, the very next stage, all of y was exhausted and it returned u. Then let h be just this h0 restricted to alpha. Right, so it's the interesting bit of h0 before it starts returning u all the time. So what does h do? It sends the ordinals less than alpha one-to-one onto y. So it's a bijection between alpha and y. So now I'm home and dry. I can impose the well ordering on y, which this enumeration gave me. So perhaps unnecessarily. Right? Then we have a well order R on y, which is kind of immediate from this enumeration. But I'll take, let's see, PRQ for P and Y, if and only if h to the minus 1 of P is less than h to the minus 1 of Q. Right. So the stage which P is enumerated comes before the stage that Q is enumerated. Okay. So that then becomes an order preserving map between alpha and YR. Given by this h to the minus 1. So we well ordered y. As y was arbitrary, that gives us WP. So that finishes the left to right direction there. Okay, any questions? So we'll finish off then by doing the right to left. Here, we'll suppose the well ordering principle we need a choice function for an arbitrary collection of non-empty sets. So we let A be the union of the things in G. So here's G, which is our bag of bags here with all of its elements. A is just the collection of all of the elements of these elements of G. So it's just obtained by rubbing out these lines here. By the well ordering principle, there's a well ordering of A. So I can find some well ordering of A here. And we need a choice function. Well, the choice function is the one kind of staring us in our face. Now that we can well order the things in all of the sets inside G, we can just take the least one in the set we're interested in. Okay, for X, so pick an X in G here. We'll just define f of X be the R least element of X. And because all the elements of X, of course, are in A. And it says in the notes, check that this works, but I think there's absolutely nothing to do. I mean, by definition, it works, right? We've taken the R least element of our collection of all the elements of the sets like X, and that's fine. So I think this finishes. I don't think you have to say. I don't think there's much more to check there. Okay, so that finishes the equivalence of AC with the well ordering principle. And what we'll do next time, so in the recorded lecture, will be the equivalence of the well ordering principle with AC with Zorn's lemma. Right? That's a little bit more tricky because it involves looking at chains of sets. Right? But that should be all for next time.